NASA engineers make plans for the ISS Mimic available on GitHub. New stretchable skin lets robots feel. And finally, an update on Spot, the robot dog. Stick around to find out more in this episode of News Bytes. Hello and welcome to Advanced Ingenuity Labs, your insight into technology. I'm your host, Aisha Sharif, and this is News Bytes, where we cover innovative developments in the latest technologies. It's hard to believe that the International Space Station, the largest multinational space project, has been continuously occupied since November 2nd, 2000. The International Space Station has welcomed 240 individuals from 19 countries and has conducted 3,000 global research projects for researchers and students alike. To celebrate the success of the orbiting space station and 20 years of continuous human occupation, a group of NASA engineers has built the ISS Mimic and have just published their instructions and code on GitHub. The ISS Mimic is a 1% scale model of the International Space Station. The ISS Mimic has 12 motors, 10 to control the solar panels and 2 to turn the thermal radiators. The motors receive live data streaming from the International Space Station. In other words, what you see on the ISS Mimic is what's actually happening in real time on the space station. A Raspberry Pi is used to display the telemetry from NASA's public live ISS data stream in a more interesting and engaging format, rather than just showing a bunch of numbers. Arduino microcontrollers are used to receive data from the Raspberry Pi in order to control the 3D printed model of the ISS and make it exactly match up with the actual ISS in real time. In addition, all of the solar arrays, radiators, and the outboard truss rotate to match the ISS joint angles. The ISS Mimic uses a touchscreen to display battery charge states, electrical power generation, joint angles, communication dish status, gyroscope torques, and even airlock air pressure, which, according to the engineers, is fun to watch prior to a spacewalk. Using the touchscreen, the ISS Mimic can be activated, sending telemetry from the Raspberry Pi to the Arduino units, which in turn commands the motors in the model to rotate the solar panels and the thermal radiators into the proper angles. Using the Raspberry Pi, users can select various modes. When the ISS Mimic is in live mode, the motor commands are being received from the data stream sent from the ISS. Advanced playback mode is where prior orbit data is stored on the Raspberry Pi, is played back at 60 times faster than the original speed. Therefore, a 90-minute orbit profile would only take 90 seconds in its playback. And finally, disco mode can be used to alert users when the International Space Station is flying over, or when interesting activities are taking place on the space station. According to the engineers, the project is still a work in progress. However, the basic functionality, the ability to receive telemetry and transmit it to the Arduino units, is finished and available on GitHub. Through a shared mission, the world has come together to develop an international space station that has been successfully orbiting the Earth, conducting science experiments, housing humans, and inspiring humanity for over 20 years. Are you inspired by space exploration, the accomplishments of the International Space Station, and the opportunities provided by the Raspberry Pi Foundation and Arduino, or even other technological advances? Let me know, what inspires you? If you enjoy this video and find value in our content, You can help us by sharing it with others. Also, leave a comment as we want to hear from you, and consider liking the video and subscribing to our channel. You may also click the notification bell if you don't want to miss our upcoming videos. To stay informed about our upcoming training courses and camps here at Advanced Ingenuity Labs, visit our website at advancedingenuitylabs.com and sign up for our email notifications. Cornell researchers have created a fiber optic sensor that combines low-cost LEDs and dyes, resulting in a stretchable skin that detects deformations such as pressure, bending, and strain. This sensor could give soft robotic systems or anyone using virtual or augmented reality technology the ability to feel the world around them. This project expands on an earlier stretchable sensor created in the Organic Robotics Lab at Cornell University, in which light is sent through an optical waveguide while a photodiode detects changes in the beam's intensity to determine when the target material is deformed. For this new project, the paper's co-lead author, doctoral student Hidan Bai, drew inspiration from silica-based distributed fiber optic sensors, which detect minor wavelength shifts as a way to identify multiple properties, such as changes in humidity, temperature, and strain. Hidan Bai said, "We know that soft matters can be deformed in a very complicated combinational way, and there are a lot of deformations happening at the same time. We wanted a sensor that could decouple these." Bai's solution makes a stretchable light guide for multimodal sensing, SLIMS. This long tube contains a pair of polyurethane elastomeric cores. One core is transparent, the other is filled with absorbing dyes at multiple locations and is connected to an LED. Each core is coupled with a red, green, blue sensor chip to register geometric changes in the optical path of light. SLIMS sensors can operate with small optoelectronics that have lower resolution, which makes them less expensive, simpler to manufacture, and more easily integrated into small systems. For example, a SLIMS sensor could be incorporated into a robot's hand to detect slippage or movement. This technology is also wearable. The researchers designed a 3D printed glove with a SLIMS sensor running along each finger. The glove is powered by a lithium battery and is equipped with Bluetooth in order to transmit data to basic software, which Bai designed, that reconstructs the glove's movements and deformations in real time. The researchers are also studying how SLIMS sensors can boost virtual and augmented reality experiences. Rob Shepard, the lead researcher and associate professor of mechanical and aerospace engineering in the College of Engineering at Cornell University, said, "VR and AR immersion is based on motion capture. Touch is barely there at all. Let's say you want to have an augmented reality simulation that teaches you how to fix your car or change a tire. If you had a glove or something that could measure pressure as well as motion, that augmented reality visualization could say, 'Turn and then stop,' so you don't over-tighten your lug nuts. There's nothing out there that does that right now, but this is an avenue to do it." Currently, the researchers are working to incorporate this technology into physical therapy and sports medicine. Both fields have leveraged motion tracking technology, but until now have lacked the ability to capture force interactions. Let's end this episode with an update on Spot the robot dog. He has been spotted in the wild yet again, this time at a construction site. As part of Boston Dynamics' early adopter program, Foster and Partners, an architectural design and engineering firm, have been exploring the use of Spot as a tool to capture and monitor progress on construction sites. Foster and Partners Applied Research and Development Group has been working with Boston Dynamics to explore the potential of a robot in a dynamic environment, such as a construction site, capturing changes on a regular basis and being able to easily compare the as-designed construction models against the as-built reality. With the continuous changes that occur on construction sites, the need to track and measure these changes are of vital importance. Since the demand to capture errors early is essential in order to make the necessary corrections and to be able to stay on schedule and within budget. Tracking, measuring, and sequential scanning is a time-consuming process that can take hours or even days, and as a result, may produce scans that can't be compared directly against each other. Spot can be controlled remotely, is versatile across many terrains, and can also repeatedly follow a pre-mapped route, making it an optimal tool to be used in scanning building sites on a regular basis with minimum resources and time. Using one of their current projects, the team created a map to approximately guide Spot within the areas that require scans and specific data collection. Spot repeated the mission weekly in order to yield a sequence of highly comparable and consistent models. Martha Sigkari, partner at Foster and Partners, said, "The ability of Spot to repeatedly and effortlessly complete routine scans in an ever-changing environment was invaluable, not only in terms of the consistency, but also the large amount of high-quality data collected. Through this process, we developed a sequence of scans that may help us track the project progress against timeframes as well as facilitate regular comparisons against the BIM models. Our scans can ensure that very quick and accurate changes to the newly designed system could be made to accommodate the differences captured by the scans, all in a matter of days. This could result in savings both in terms of time and money." The practice's own campus and Battersea Power Station proved to be an ideal testing ground for the project, and the client and construction teams were supportive of it. Scott Grant, head of Phase 3 at Battersea Power Station, said, "We were delighted to assist Foster and Partners in using Battersea Roof Gardens as a test bed for Spot. The team explained how the robot can be used on a construction site and the various benefits it could bring. We were excited to see it in action and have enjoyed having Spot on site." That's it for this episode of News Bytes. As always, if you enjoy this video and want more, leave me a comment and consider liking and subscribing. See you next time.